So in this part, we will be looking into paging, basically different type of dynamic memory allocation. Uh, instead of in previous part, we looked into segments. In this part, we'll be looking into pages. So what is the main problem with using segments? As we saw, it's external fragmentation, right? Because we could have we could have holes in the memory in combination that could be big enough to store a segment. Since they are not contiguous, we cannot use it. So one way this can be solved is to use a smart allocator. That means, so instead of randomly assigning holes, like randomly assigning memory chunks, a smart allocator can allocate segments to different regions of the memory based on the availability of free space. Like, so there are many different allocation algorithms. Like the two most commonly used are best fit and first fit. So best fit is when you have uh, when you have a list of holes, it actually picks the smallest hole which is big enough for a given segment. Okay. In case of first fit, it just maintains a list of free holes and it will just pick the the first chunk that is big enough. So it will not check for the smallest chunk, rather it will just pick the first chunk that is big enough. So best fit is not necessarily better than first fit. In most cases, it is better, but not always. Let's consider an example where we have two free blocks. First block of size 20 and second block is of size 15. So if we get allocation requests of block 10 and 20, you can imagine that best fit will perform better. Basically, uh, there will be less space wasted. Okay. Whereas in case of another request where we have requests for blocks of size 8, 12, and 12, here both best fit and first fit performs equally well. So neither of the two allocation algorithms win. So, a more deeper analysis shows that first fit tends to leave average sized holes, like all unused, whereas best fit tends to leave some very large holes and some very small holes, because it may pick the biggest chunk, biggest hole, although small hole is needed. So but in reality, what happens is, if your storage is running out, or rather if your storage is close to running out, it doesn't matter which allocation algorithm you pick, you would it n- none of them are efficient. Okay. So the most commonly used technique is use the easiest solution, mostly first fit. Okay. So the way segmentation is implemented in the operating system, as we briefly saw this in the previous part, where operating system maintains, for each process, we maintain a segmentation table in the process control block. So when creating a process, we also allocate space for the segments, and we will fill the process control block with the bases and bounds. So when the process dies, we also need to return the physical space used to store segments. And then we also need to mark the corresponding physical pages to be free, like pools of physical memory to be free. Then what should operating system do during context switch? Simple, right? So we need to first save the context table of the current running process and load the new segment table of the new process. And what about context switching between threads? So here operating system can be smart. Rather than switching everything, operating system can see if the threads belong to the same process. In that case, it just needs to switch stack segment, right? It doesn't need to switch all the segments, because all the segments will be the same because they belong to the same process. So so context switch between threads of same process will be cheaper than context switch between threads that belong to different processes, just because the amount of work operating system has to do uh, for segment, like for loading new segments, is less. So as I mentioned before, we will store all the segmentation info or like the segment table in the memory under memory management info of process control block. So, and operating system can provide various operations in managing segments. For instance, a process can ask to increase a segment, like to increase the size of the segment, in which case there are multiple options operating system can explore. The simplest option is to see if there is space available. Basically, if there is space available in the corresponding physical segment above and below, if it is available, then just change the bound, right? Just change the bound in the segmentation table of that particular segment. If the space is not available, then operating system can move the segment to a bigger whole, well, rather bigger chunk. So, and what happens when there is no space available to allocate a new segment? So in this case, operating system can do what we call compaction. In this, what operating system can basically move the segments around in the physical memory. These segments could belong to different processes, but it can move the segments around and update the corresponding segment table of the processes. And then it can have bigger chunk. Basically, it can solve the external fragmentation problem by moving the segments around. This process is usually called compaction. However, compaction is expensive because each segment that it has to move, it needs to update the segment table of the corresponding processes. So a summary of different segment, like different dynamic memory management schemes using segments is shown on the slide. So here top two are basically static relocation, where there is no dynamic memory translation, whereas the bottom two, the base and bound and the multiple segments method, these two methods are dynamic memory reallocation techniques. Here we saw like these two techniques have various pros and cons. And one common disadvantage of all the segmentation based memory management techniques is external fragmentation. So what fundamentally causes external fragmentation, right? The main reason is because segments can be of different sizes. So each process can have a segment of different sizes, and each segment within a process could be of different size. Okay. And furthermore, each segment has to be allocated contiguously. So this leads to external fragmentation. These are the two fundamental reasons for external fragmentation. So how can we avoid it? Pages. We can use pages. So what does pages mean? So pages is a fixed size memory unit. So we divide the entire virtual address space of the process and even the physical memory that is available to us into fixed size chunks. We call them pages. Okay. So even the virtual address space of the process is divided into pages. Similarly, physical memory is divided into pages. Now the allocation or memory management happens in terms of pages. So this actually has many advantages. So it makes allocation and like restoring, like swapping easier. So we'll be looking at swapping more in the next lecture. But one thing to note here is basically allocating a memory is quick, and it reduces memory fragmentation because now all the memory chunks are of same size. So there is very less, like, I mean, there is almost no chance of having bigger or smaller holes because all holes are of same size, right? And similar to segmentation, so paging can be implemented by using a page table. Okay. Where, I mean, another way to look at paging is segmentation, where all segments are of same size and every process has bunch of segments and each segment is of same size across all the processes. Okay. And those segments we call pages. And instead of segmentation table, we have page table here, where page table similar to segmentation table, defines the base address for each page. And then we don't need to store the offset here because we know every page is of same size. So that's also another advantage here, because since we know that all pages are of same size, we just need to store the base address of the page. Okay. And then we also can store permission bits, which says whether the process can read or write the corresponding page. And translation, it's very easy. We don't need to see, I mean, one thing to note here is there is no size component involved with each page. Whereas in case of segment, there was a size component. So translation is very simple, similar to segmentation. So whenever we get virtual address, we have the top bits that indicate the virtual page number. So we have a page table. We use the page virtual page number as an index into the page table. We get the corresponding physical page number, and we just use the offset from the virtual address. We append the offset to the physical page number. That's the physical address. If the process tries to access outside its virtual address, we see that if virtual page number, if it is greater than page table size, which indicates the number of entries in the page table, then we throw an error. Okay. And context switch, when context switch happens, the same maintenance that needs to be done for segmentation also needs to be done for the paging, basically storing the page table and reloading the page table of the new process. So what are the advantages? Very easy to allocate memory, easy to swap, and easy to share, because now processes can now share memory at very fine grained, basically at page level, right? So translation, as I mentioned, we just look up in the page table and we get the corresponding physical page number and append the offset. That's it. And this is possible because all pages are of same size. And as I mentioned, this cannot be done in segmentation because segments could be of different sizes. So using pages actually reduces complexity of memory translation. Okay. However, uh, we pay price in different aspect. Basically, now we need to store page table entries. So PTE stands for page table entry. So here, assume that each page is of 4 kilobyte size. I mean, that's the common page size that is that all the operating systems use nowadays. So what's the worst case for 32-bit address machine? That means, like, in worst case, what is this amount of memory required by the operating system to store all the page table entries, right? So for each process, in worst case, we need to store 2 power 20 page table entries, because each page is of 4 kilobyte size, which is 12 bits. So if we subtract 12 bits from 32, you get 20. So those many entries we need to cover the entire address space for each process. So now we multiply that number into number of processes. Similarly, for 64-bit machine, you do the same thing. Like, how many page table entries are needed? Here, yeah, you subtract 12 from 64. Okay, you get 52, and so 2 power 52 into number of processes. So that's the maximum number of page table entries in that operating system that deals with 64-bit machine needs to store. So one thing is, where do we store the page table? Of course, we'll store it in the memory, but when it comes to CPU, where do we store? So most of the CPUs, like most of the CPU manufacturers, they provide this additional unit called memory management unit, which actually deals with all the memory management. Basically, the translation table, or like the translation hardware, is called memory management unit. So even the small page tables are too large to load into this translation hardware or memory management unit, because you can imagine that uh, one page table of, of the entire process could be 4 MB. So here, even loading the entire 4 MB into memory management unit at every context switch is just too expensive. Okay. So what happens is memory management unit just stores the base address of the page table. It doesn't store all the entries, rather it just stores the base address of the page table. That way, so when uh, when a virtual address comes, it actually indexes, it uses the page table base address and then indexes the page table by fetching the corresponding entry, right? Once it knows the page table base address, it can figure out, like given a page number, it can figure out the corresponding entry, then it can fetch the corresponding page table entry from the physical memory, right? Actually, in reality, how it works is there is another piece of software between, another piece of rather hardware between MMU and physical memory called translation look aside buffer. We will be looking into translation look aside buffer in the next lecture. But just remember that there is a cache of page table entries between MMU and physical memory. And then one thing to note here is, depending on the page size, the size of page tables changes, right? So commonly used pages is of size 4 KB. However, you can have large pages too, right? You can have pages of size 8 KB, in which case you will have small table, but it leads to internal fragmentation. That means if the process has to use, let's say, 1 KB, but if if the page size is 8 KB, then 7 KB will be wasted. So this is called internal fragmentation. And few comparisons between paging and segmentation. Segmentation is is good, in which case it allows processes to efficiently use their memory, right? There is no internal fragmentation whatsoever, because you can actually ask for the exact amount of memory that you need. Okay, you will be given. So each segment is of, can be of size uh, anything, right? And then the allocation is complicated, because we need to find a smart allocator, try to find a better hole in the memory. So allocation is complicated. And then it leads to, segmentation leads to external fragmentation. Whereas in case of paging, uh, the allocation is easier and swapping everything is easier. However, there could be, the page table size is huge, because again, as I mentioned, each page is of, mostly is of size 4 KB. So for each process, in worst case, there is 2 × 20 entries in the page table. So there is overhead there. And another problem with paging is internal fragmentation. That means even if the process needs just 1 KB, it will get 4 KB. So the unit of allocation is 4 KB. So this leads to the problem where process might be underutilizing certain pages. Right? If let's say a process needs only 1 KB, but it will be given at least 4 KB. So in which case you can see that 3 KB is unused. So this is called internal fragmentation. So in the next lecture, we'll be going into more details about paging, and we'll see how exactly paging is implemented at operating system level, and what are the hardware components that help operating system in doing it more efficiently. Thank you.